you may have a question in your mind is, what are applications of derivative in two dimensions, right? Because if you remember in calculus 1, when you learn differentiation with Ajahn Tirapong in calculus 1, if you remember, you can use differentiation to approximate the value of the function. And also you can use differentiation to solve the optimization problem, because you can just differentiate one time, set it equal to 0, and then you solve for something called a critical point, and then you can go for maximum and minimum value of the function from there. So that is the idea from calculus 1. Well, the idea here in calculus 2 is we trying to copy the idea from calculus 1, but now we are going to view it in two dimensions. So before we head to the total the differential content, so let me review you the content from calculus 1. In calculus 1, we define differential of f. The differential of f in cal 1, this is defined to be df. It's just d and then f. Well, this is defined to be f prime x dx. This is the total, this is the differential from cal 1. Just f prime x dx. And then when you have differential in cal 1, the application that you have is you can approximate the function f by using the equation f x plus dx. It can be approximate by fx plus dfx, which is the one that I box it, which is the same thing with fx plus f prime x dx. Well, this is what you learn in calculus 1. So you learn that when you have a function f, right, and then you want to approximate at the value fx plus dx, you can use the equation to approximate it to be fx plus f prime x dx. For example, so let me recall you, because this is way like far, like few months ago when you learn calculus 1 with Ajahn Tirapong. So for example, in calculus 1, if I ask you to approximate, for example, so if I ask you to approximate, let's say 16.02, and then the fourth root of 16.02, you can see from this question that, well, you know and you have the idea in your mind that if you take the fourth root of the 16, you're gonna get if you take the fourth root of 16, you're gonna get 2, right? You're gonna get 2, right? Because 2 raised to the fourth power, you get 16. So 16.02, if you take the fourth root, you should get 2 and a little bit something. So in calculus 1, we say that, hey, you can observe that 16.02, this is 16 plus 0.02. Well, the term that you have, the term that you exceed number 16, you have only just 0.02, right? And then here in calculus 1, we say that we can view this thing as 16 as your x, right? And then you can view 0.02 as your dx. And then in cal 1, we say, hey, why don't we set fx to be x to the 1/4 here? And once you set up fx equal to x to the 1/4 here, then we need to find f of 16.02, right? This is what we want. And then, well, to compute f 16.02, you can compute it by say that this is f 16.0.02. And by the approximation, you can say that this is approximate f16 plus f prime at 16 multiply 0.02. So what I did here is just I have fx plus dx here, x plus dx, and then I say I use the approximate equation. So this is going to be fx plus f prime x, right? This is f prime x, and then multiply dx. Does it make sense? This is what you did in Cal 1. You probably forgot it already. That's fine. So I recall you that this is what you did in calculus 1. And then you have f16 here. This is going to be 16 raised to the 1 over 4. And then here, f prime 16. So you have to differentiate f one time first. So you're going to get 1 over 4 and then x to the 1 over 4 minus 1 here. And then when you plug in the number f prime of 16, so you're going to get 1 over 4, 16 to the negative 3 over 4, right? And then you just put it in here and then multiply 0.02. Well, this is what you did in Cal 1, and then, well, we're not going to compute this thing again, but, well, this is the idea. So you can see that the main idea of the total, of the differential in calculus 1 is when you have a term that you want to approximate, you can just trying to look at the term inside here, and then you're trying to manipulate it as something that you know, that the number that you are familiar with, and then you add or subtract something that is just, exceed the thing that you already know. And then after that, you put it into the equation, and then you're going to get the approximation. Well, the idea here is for calculus 2, this is what are we going to do. So we have function of two variable fx, y. This is a function that we have. So we are going to define the total differential. So because this is the function of two variable, so we're going to name it differential in two dimension. But differential in two dimension gonna call total differential. So you just add the adjective to it, and then you call this thing total derivative. And then here we're gonna define something called dfxy. This is the total derivative. This is called total derivative or total differential. Well, I think I'm gonna use total differential because it is the same as in the book. So total differential here, and total differential is defined to be, well, let's look at that. This is the definition of total differential. So the notation going to be dc or df, doesn't matter. Sometimes you use df, sometimes you use dc, but, well, I am more familiar with df. So df xy, this is a total differential. This is going to be equal to f subscript x. That means you have to differentiate f with respect to x, and then dx, and then plus f differentiate with respect to y, dy. All right, this is a definition of total differential. Total differential. This is the definition. All right, when you do it, when you trying to do it on the approximation, you're gonna have an approximation equation as well. So this is the approximation. So the approximation equation, if you have fx plus dx and y plus dy, look at that. Well, you can approximate it by f at the point x, y, and then add them by the total differential. This is going to be f x, y, and then plus f subscript x, x, y, dx, and then plus f subscript y, x, y, dy. All right. one more time. So the approximation here, you can approximate by that equation. You can see that this is the same pattern in calculus 1 because you're gonna look at the point x, y that you know how to compute it easily, and then you put it on the first term. And then after that, the remaining term going to be just total differential. And then the total differential here, by definition, it's going to be f subscript x dx plus f subscript y dy. So this is all the theory that you need to memorize for this content. Well, I have 2 examples coming up for you, and hopefully after you see 2 examples, you will get more sense of this application. Hopefully. All right, so we're gonna go to 2 approximation examples. Sounds good? All right. Any questions? All right. Well, if you have any question, you can stop me at any time. I already told you. All right. So example 34. Well, this is the similar thing that I am going to ask you on the final exam as well. So use total differentials to approximate this one. So the idea of this question is we are trying to approximate this thing. Well, the one thing is that you can see that, okay, if you have calculator, you can compute that thing easily. But in calculus, we learn how to do this question without calculator. We're trying to appreciate the application of differentiation. So we are going to do this one without using calculator. And then you will see that you can do this one by hand without using calculator. And you're going to get the approximation of this term. All right, so let me show you how to do this question. So first of all, you can see that the term that you have here, square root this thing. So you can see that if you make an observation, you're going to see that this number is very close to number 3. This is very close to 4. Right? So it's close to 3 and close to 4. So actually the number that you get at the end, you should get something that is close to 3 and close to 4 here, which is going to make the work easier for you because you're going to get 9 plus 16 here, and then you get square root 25, which is 5. So at the end, if you can compute square root 3 square plus 4 square here, it's going to give you number 5, which is the easy one. So we're going to use the approximation by trying to make this term fit into our approximation equation. So the idea is we are going to let the function f to be square root x squared plus y squared. Well, this is my function f. Well, you can see that we want to find f 0.03, 3.98. This is what we want. Well, observe that. Well, you can see that the number 3.04, this is actually 3.0.04. And then number 3.98, this is actually 4 plus negative 0.02, right? So the reason why I wrote this thing, because, well, the thing that I highlight in orange here, 3.0.04, this is going to be my x. This is going to be my dx. And the thing that I highlight in red here, 4 and negative 0.02, this is going to be my y and my dy. Well, before doing the approximation equation, you should have this thing in your head. This is my x, this is my y, this is my dx, this is my dy. And then when you do the equation, you're going to do f 3.04, 3.98. This is what you want. So this is going to be f of 3.0.04, 4 plus negative 0.02. right? And then by the approximation equation, you have fx plus dx and fy plus dy. So you're gonna get approximated by fxy, which is f34, and then plus f subscript x at 34, and then you multiply 0.04, and then plus f subscript y at 34, and then you multiply negative 0.02. So if you have a hard time to memorize, to follow me, so you can see that this is my x, this is my dx, this is my y, this is my dy. So what I get is actually at the end I get fxy, and then I get f subscript x, xy times dx, and then here I get f subscript y, xy times dy. You can see just that you do not need to be fast. You just go slow, and once you get this thing, so you can compute it. So f34, this is going to be square root 3 square plus 4 square, which you already know the value, right? And then what you need is you need f subscript x34. So that means, well, we're going to give the space here. So let's compute partial derivative. So what is going to be f subscript x? So, well, you have fxy equal to square root x squared plus y squared, which is that, to the 1/2, right? And then after that, you differentiate 1 time. So you're going to get 1/2 x squared plus y squared to the negative 1/2. And then by the chain rule, you have to differentiate inner function. Differentiate x squared plus y squared with respect to x. So you get 2x, right? And then after that, well, you cancel out number 2 here. So at the end, you're going to get x over square root x squared plus y squared. Because x squared plus y squared raised to the negative 1/2, this is 1 over square root x squared plus y squared. Well, you have f subscript x here. Similarly, you can compute f subscript y here. Well, this is going to be 1/2 x squared plus y squared to the negative 1/2, and then you differentiate inner function with respect to y, so you get 2y. The same thing to cancel out. So what you get here is you get y over square root x squared plus y squared. So the thing that you leave it on the side here, so you already have f subscript x and f subscript y. So you can plug in the number here at 3 and 4. So you get 3 over square root 3 square plus 4 square, and then multiply 0.04. And then here you're gonna get 4 over square root 3 square plus 4 square, and then negative 0.02. Well, the rest of the work, you just need to compute it, and then that would be your answer. Here you're gonna get square root 9 plus 16, right? Here you're gonna get 3 over square root 9 plus 16. And here you're gonna get 4 over square root 9 plus 16, and then negative 0.02. Well, square root 25 is 5, so this is 5. This is 3 over 5, 0.04, and then this is 4 over 5, negative 0.02. All right, and at the end, well, you compute this thing, so you're gonna get 5.008. Without using calculator, you can compute this thing. All right, sounds good. Any questions? Any of you have question on this thing? All right, sounds good. So we're gonna do one more question on approximation. Well, this supposed to be the easy question on the exam, because you have a pattern to do it. Everyone should be able to do it easily because you have a pattern to do it. All right, so we're gonna have one more example here, and then we can move to another topic. So example 35. So I want you to use the total differentials to approximate this thing. So you can see that the number that you have here, well, one more time, 7.7 8. This is a number that is close to number 8, right? Close to number 8. And 9.03 here, this is the one that close to number 9. So actually, you're going to use the differential, and then you're trying to get dx and dy by compare number 7.78 that is close to number 8 and 9.03 that is close to number 9. So we are going to do it. So let fxy equal to, well, my function gonna be the cube root of x times the square root of y. Well, if you are similar to me, so you feel, well, I am not comfortable to look at square root here. What I like is I like to say this is x to the 1/3 and y to the 1/2 here, because it's make the world easier for me to see this way, because I don't want to see cube root or square root. It's made me confused. So when you have that thing, so you can see that this is what you want. We want to compute f 7.78, 9.03, right? Well, give me the answer in the chat. What is going to be your dx and dy for this question? Well, what is going to be your dx and dy in this question? So give me in the chat. Well, Natsuki say, well, you need to question, right? Yeah, you need to answer, right? Well, Natsuki said that one. Would you agree with Natsuki, everyone? Well, just give the answer in the public chat, because well, it's gonna be your check-in for today if you leave the answer in the chat. Well, you can see that, well, everyone say yes, right? Because you say that, hey, Nida and Purohit and Natsuki, well, they claim that the x should be negative 0.22 and dy should be 0.03. Well, you can see that what you want is f of 8, and you need to see what you missed from number 8, right? Which is actually negative 0.00, negative 0.22. I went too fast. All right, you can see that. Well, I told you here, the mistake that usually the student usually make is you forgot to bring the negative side. So every time when you do this, you need to bring the negative side with you. Whoa, which is good now, because you know Purohit, Natsuki, and Nida, and everyone that will agree with the answer. So you already carry the negative side. And then the next one, you have 9 plus 0.03. Well, this topic is not hard, but you just need to be careful on the negative side that you carry out. And then the next thing is I am going to, well, now you have x dx and y dy already. So you're gonna approximate it by f at 8 and 9, right? Because this is my x and y. And then I'm gonna do f subscript x at 8 and 9. And then I'm gonna multiply the x, which is negative 0.022. Sorry, negative 0.22. I keep make a mistake on that thing. All right, so f subscript y 8, 9, and then 0.03. All right, so you can see that we need again, we need the differential, right? We need the partial derivative. So we're gonna differentiate this thing with respect to x. Well, hopefully it's easy enough. Well, we do not need to differentiate y, so I'm going to pull out y. And then I need to differentiate x, so I get 1/3 x to the negative 2/3. Can you follow me? Well, this is a little bit tough, right? Because you have x to the 1/3, so it's going to be 1/3, and then x to the 1/3 minus 1, which is x to the negative 2/3. And this thing, well, if you want to simplify a little bit, so you can say this is actually square root y times 1/3 and then cube root of x squared. All right, that is my f subscript x. All right, I'm gonna box it because I'm gonna use it later. All right, so, and then my f subscript y gonna be, well, I do not need to differentiate x, so x to the 1/3, and then for y to the 1/2, so I'm gonna differentiate to get 1/2 y to the -1/2, and that gonna give me the cube root of x times 1/2 square root y. All right, that is my f subscript y. All right, so it seems that you have all components already. So now you just plug in the number. All right, let's do it. So f8 and 9, this is going to be the cube root of 8 times the square root of 9. All right, that is f of 8 and 9. Right, and then f subscript x at 8 and 9. So you're gonna get square root 9 times 1/3. Well, you have to be careful when you plug in the number. So 8 and 9 here, so 1/3. So here the cube root of x squared is 64, right? F subscript y here, this is going to be the cube root of 8, and then 1/2. Square root y here going to be square root, my y here is 9. All right, 0.03. All right, well, again, you have to be careful a lot when you plug in the number because the number look messy now. The cube root of 8 is 2. The square root of 9 is 3. All right, the square root of 9 is 3. 1/3 here. The cube root of 64, this is 4, right? Because 4 times 4 times 4, 3 times, you're gonna get 64. All right, and then -0.22 here, and then plus cube root of 8, you get 2, and then square root of 9, you get 3. All right, so you can cancel number 3 here, cancel number 2 here. So you're gonna get 6 plus -0.22/4, and then plus -0.03. Plus no negative here, plus 0.03/3. All right. At the end, you get 6 minus 0.055, and then plus 0.01, which is actually 5.955. Well, you can see that you can approximate it. You see, you do not need to use calculator at all, but you can compute this thing by hand. Nowadays, it is a lot easier for us because nowadays we have Google, we have calculator, we have everything that you can just click, just type something and click. That's all for 2021. But if you go back to the 19th century, it's gonna be a lot harder to approximate this thing, and you have to use differentiation. All right, so that is the first application of differentiation in 2 dimensions. Well, again, on the exam, on the final exam, so I'm gonna ask one question for you to approximate the function. So I just want you to compute it by hand and show me, like example 35 and 34. So just start it. So again, on the final exam, maybe you have to go back to study this question a little bit because it's going to be 4 or 5 points on the final exam. Sounds good? So for those of you who are already in, again, so type in the chat again. Give me the point out of 10 to yourself. How would you grade yourself for this topic, the differential? Well, 7, 8, 9, 10, or less on that thing, you can give it to yourself. This topic is easy, everyone. So you should be comfortable. You feel like you can follow this thing. All right. Well, sounds good, everyone. All right. Okay, hopefully you find this is not way too hard for you, huh? So the only hard part gonna be the one when you differentiate, because if you differentiate, sometimes the function look messy, right? And then you have a hard time to differentiate. But I am not going to give you a tough function to differentiate. So the function that I want you to differentiate is going to be the one that is easy enough for you to differentiate. All right, so that is the first application. All right, well, let's talk a little bit about minimum and maximum value, and then I will give you a break, okay? So when it's close to 11 a.m., I will give you a 5-minute break. Okay, so the next topic is maximum and minimum value. This is our last topic for this chapter. Another application of derivative from calculus 1 that we use a lot, we appreciate a lot, is finding maximum and minimum value. So first of all, again, let me review you what you have in Cal 1. So in Cal 1, when you have fx here, what if I want max and min? What would you do in Cal 1? So in Cal 1, you say, hey, when you have fx, Ajahn, I am going to differentiate f prime x, right? This is what you did in Cal 1. And then, well, once you differentiate in f prime x, you set up f prime x equal to 0. And then you find all the points x that satisfies f prime x equal to 0. This is going to call the critical number, right? If you remember, so you have critical number here. And then after that, the critical number here gonna be the one that is your candidate. They are candidates for maximum and minimum, right? This thing gonna be candidates for max and min. And then you can check if it is max and min by using the second derivative test, or you can look at the graph of f prime. You have so many ways to check that the critical number actually give you max or min, or it could be the case that it doesn't give you max and min. Sounds good? For example, in calculus 1, this is what we just did in cal 1. Well, suppose you have fx equal to, let's say x squared plus 3x plus 5, and you want the maximum value of this function. So you can say you differentiate one time, so you get to x plus 3. And then once you differentiate one time, you can set it up equal to 0. You set this thing equal to 0, which give you to x plus 3 equal to 0. And then you solve x equal to negative 3 over 2, right? Which means x equal to negative 3 over 2. This is actually going to be something you call critical number. And your critical number here gonna be the one that is your candidate for max and min. And your x equal to negative 3 over 2. Well, one thing when we learn in Cal 1, you can differentiate one more time. If you differentiate f one more time, you get f double prime x, and you get 2, right? F double prime x. Well, if your f double prime here less than 0, you're gonna get maximum. And if your f double prime greater than 0, you're gonna get minimum. Well, here x equal to negative 3 over 2, but you can see from the second derivative test, the pattern gonna give you here, this is going to be your minimum. This is the point that give you minimum. It give a minimum, right? Because you compute f double prime at negative 3 over 2, and then you get number 2, which is less than 0. Which is bigger than 0. So that is the critical number that give you a minimum. Sounds good? Hopefully are you familiar with this thing? I think you are familiar with this thing, because, well, if you feel like you already forgot it, just recall it. When you learn Cal 1, you did this thing before. You have a function f, you differentiate one time, and then you set it equal to 0. You solve for critical number, and then after that you get the candidate for max and min, and after that you have few ways to check that those points are actually max and min. Now we are trying to extend the concept into 2 dimensions. Okay, we are trying to extend the concept into 2 dimensions. So first of all, you have to be careful about the word local maximum and absolute maximum. So when I say local minimum or local maximum, this is going to be the point that is actually maximum and minimum compared to its neighborhood. So when I say local maximum, it's just going to be it is a maximum compared to the, to the neighborhood near them. Neighborhood, that neighborhood. Yeah. Next, I have local minimum. Local minimum here, this is the point that it is actually a minimum compared to the point nearby. So you could have so many local maximum and local minimum, but you will have only one absolute maximum and one absolute minimum if it exists. Because when you say absolute maximum, it means it is a maximum like compared to the entire domain. This is the maximum value. Does it make sense? Well, when we say absolute just give you a sense that, hey, this is just max or min compared to any point in the domain, like all the point in the domain, just compare it, and which one is maximum, that will call absolute maximum, and the same thing, which one is the least, that is called the absolute minimum. But local, you just compare to its neighborhood. All right, that is the definition of local max and local min, and absolute max and absolute min. So in the box here, I just copy from the book. In the box here, I just copy from the book. You can read it by yourself, but this is the same thing as I just told you from the picture. Well, local maximum and local minimum, you compare to the point nearby, but absolute max and absolute min, you compare to the entire domain. So actually, when you want to compare absolute max, absolute min, you have to compare it to the the whole domain. Well, similar to 1 dimension, if f has local max or local minimum at the point AB, well, the first order partial derivative of f exists, then we know that f subscript x is equal to 0 and f subscript y equal to 0. And those points that you have the property that f subscript x equal to 0 and f subscript y equal to 0, we're gonna call it critical point. Does it make sense? So in calculus 1, well, I'll go back here. In calculus 1, the number that you compute f prime x equal to 0, this is called critical number. This is in 1 dimension. In 2 dimension, if the partial derivative of f with respect to x is equal to 0 and partial derivative of f with respect to y equal to 0, you call that thing critical point. We are not going to call critical number anymore because this is going to be a point. So we call critical point because you are looking at the point AB. So this is the critical point, or sometimes stationary point. But well, critical point is more common, so we can use critical point here. Again, a critical point. My abbreviation PT is point. A critical point AB is a point AB such that, well, you have 2 conditions. F subscript x at AB must be 0 and f subscript y at AB must be 0. So you need 2 conditions here and here. Well, and the same concept, the critical point gonna be all candidates for max and min. At a critical point, a function could have a local max or a local min or neither. Sounds good. So, well, the same thing as in calculus 1. When you get a critical point, you have a chance that it will give you max, min, or not max and not min. Well, it could be any case. All right. So how do we know that it's going to give me max or min or, neither? So we are going to look at, let me see. Let me explain the thing in the box here first, and then we're going to have a break, and then we're going to come back to do examples. All right. That would be better. So give me more 5 more minutes, and then I'm going to give you a break. All right. Well, the thing that we use to check if the critical point give you maximum or minimum is going to call the second derivative test. So the second derivative test in 2 dimensions. So here, look at the statement. Well, suppose that you have a second partial derivative of f that are continuous on the disk with the center AB. So this is the introduction. You need to have that condition. Well, and suppose that the partial derivative with respect to x is 0, the partial derivative with respect to y is 0 at the point AB. Well, that means the AB is the critical point of f. So those are just the introduction part. Well, let's look at the main part. The main part say that if you have a critical point already, so this is what you should do. So when you have the critical point already, so you compute it f subscript xx, f subscript yy, and then f subscript xy, and then you just make a combination between them. D here is equal to f subscript x times f subscript yy minus f subscript xy square. Well, which means if you have function f, you need to compute fxx, fyy, and fxy. You just compute it first, and then after that you have fxx at the point AB. The value you get, you multiply with the fyy at the point AB, and then you subtract fxy at the point AB square. Once you have everything here, you say this is your D. This is the statement. Your D here going to be fxx minus fxx times fyy minus fxy square. Well, in short, when you memorize it, you can memorize just fxx fyy minus fxy square. Well, this is how you can just keep it clean and memorize it. This is just how you memorize it. And then once you get your D here, so the theorem say that you can compare D here with the number 0. Is the number D greater than 0? It's going to give you minimum. Oh, 1 second. If D greater than 0 and your fxx here greater than 0 as well, 2 things, so you're going to get a local minimum. If you have D greater than 0 and fxx less than 0, you're going to get a local maximum. So when D is positive, D could be max or min. Okay, it depends on the sign of f subscript xx, and then another part of this theorem say that, but if you get D less than 0, this is going to be the case that FAB is not a local max or local min. We have the name for condition C. So in case C, the point AB is called a saddle point. A saddle point, this is going to be the point that it is not local maximum and it is not local minimum, but it is a critical point. Well, you're going to see the picture pretty soon, and Note number 2, if d is equal to 0, the test gives no information. So if you compute your d and you get 0, so actually this is the case that, hey, no information. So you cannot conclude anything from there. So you have to use another theorem, which another theorem is harder. And this is outside the range of calculus 2. So for the question that you have in this class, your d gonna be positive or negative for sure. Because d is equal to 0, this is inconclusive. So you cannot solve by using the second derivative test. Another way to memorize your d here, if you are familiar with matrix determinant, so you can memorize this way, right? Fxx, Fyy, and then Fxy and Fyx. And it's similar to the thing that you compute the determinant, which is you are going to get Fxx, Fyy minus Fxy squared. Actually, the notation D stands for discriminant. Well, but if you feel like you are okay to memorize the formula directly without using the determinant, that's fine. This is just the way some people, they are more comfortable to memorize using the determinant thing, but well, it is not mandatory for you. All right, so we're gonna have, I think, 8-minute break. So we're gonna come back at 11:05, everyone. So we're gonna come back and look at some examples, and we're gonna complete the lecture today. Sounds good? All right, when we come back, we're gonna look at the example how to find the critical point and max and min for this topic. All right, so let's do a break now. 7-minute break actually. So come back at 11:05, everyone. Thank you. All right, in the meantime, you have a question, leave the question in the chat. I'll be back. All right, 11:05, everyone. All right, so we're gonna come back to our content. So the second half for today, we are going to talk about examples. So I plan to give you, well, let's go back to the slide here. So we are trying to do example here, 36, 37, 38, 39, and keep going. Whoa, all right. Maybe we should finish at least up to example 39, and we can come back to 40 on Monday, and that's all. All right. All right, example 36. So let's do it, everyone. Well, this is not hard. Again, before the break, I told you that when you have a function fxy, well, what you should do when you want to find max or min. So this is the review. What you should do is when you have fxy, so you differentiate first. Differentiate. If you differentiate, well, when I say differentiate, that means you need to find f subscript x and f subscript y. Once you find f subscript x and f subscript y, so you set it equal to 0. Well, the reason why you set it equal to 0 because this is step 1. Step 1, you find that. Oh, I'm gonna say it again. So step 1, you find partial derivatives. Step 2, you set up the equation fx equal to 0 and fy equal to 0. This is because you want to find critical point. So the idea is you're trying to get the critical point. So once you get the critical point, step 3, you can use the second derivative test. The second derivative test. So the second derivative test, that means you compute your d, which is equal to fxx fyy minus fxy squared. And then you make a conclusion from there. All right. Ready to see example? All right, example 36. Suppose I have a function here. And okay, first of all, when you have a function here, you can see this is a function of 2 variables, right? This is a function of 2 variables, x and y. Okay. The function looks a little bit complicated. However, if you differentiate one time, so you differentiate with respect to x, So you get 2x minus 2. You can see you differentiate x squared, you get 2x. Y is constant, you get 0. Differentiate negative 2x, you get negative 2. Differentiate the remaining term. This is something that does not depend on x. So good, they are all constant. All right, the same thing with f subscript y here. So that I am going to focus only the term that depends on y, which is y squared here. I differentiate, I get 2y. And then negative 6y, I differentiate, I get negative 6. Other than that, constant, constant, constant. So go to 0. All right, next, once you have f subscript x and f subscript y. So, well, in the book, they say that these partial derivatives are equal to 0 when x equal to 1 and y equal to 3. So here, actually, what we did is just we set up 2x minus 2 equal to 0 and 2y minus 6 equal to 0. So once you get that, you can solve for x and y. So x is equal to 1 and y equal to 3, right? Which means 1 and 3 here. This is a critical point. This is your candidate for max and min. How do you know that it is the candidate for max and min? Well, you see from the picture here, the picture that I have here, I just copied from the book. Well, if you look at the picture, you're going to see that at x equal to 1, y equal to 3, fxy going to be 4 here. Well, the picture, you can see that this point is going to be the bottom of, you know, the how to say, the bowl. This is the bowl, huh? The bottom of the bowl. Actually, this is going to be a local minimum. However, let's suppose that you don't have a picture. Suppose that you don't have a picture. How do you know that this is going to be a minimum? So once you get a critical point, so you can compute. Well, from here, you can compute f double prime xx first. Well, that means you carry the thing that you have on the previous step and you differentiate one more time. So you're going to get 2 with respect to x. And then if I have fyy here, so I have that, right? And then I differentiate one more time. So I get 2. And then fxy, well, you carry that. And then you differentiate with respect to y on the second time, which is 0. Because there's no y left. Well, you can compute fyx as well. They're going to give you the same thing. Because the Carroll theorem that we just learned last week or something. Does it make sense? And then after that, you can compute your d here. Well, I leave it on the slide here. This is how we compute that. And then, all right, d here going to be fxx times fyy minus fxy squared, which is going to be 2 times 2 minus 0 squared, which is 4. You can see d greater than 0. Well, go back to the theorem. Hey, d greater than 0. It's going to be case A or B. Now, next, if f double prime xx bigger than 0, it's going to be minimum. If f double prime x is less than 0, it's going to be maximum. Okay. This is what we have to focus, this thing. Oh, it's positive. So f double prime x greater than 0, right? Because it's equal to 2 and greater than 0. So by the second derivative test, one, 3 here, give a local minimum. So the 0.13 here gonna give you a minimum because the second derivative test, you already show that d here greater than 0 and f double prime fxx here greater than 0. So that is how you make a conclusion. Sounds good? All right, so we have, I think, 3 or 4 more examples. So you're gonna do this thing again and again. And you do expect to see the question like this on the exam as well, the final exam. Gonna be one question on max and min. Well, I will give you a function and I ask you to find critical point and identify that the critical point you obtain is max or min or neither. Well, actually, the next example, we are going to show you the case that when you get the critical point and it is not a local maximum, and also it is not a local maximum. All right, so I'm gonna do example 37. Well, you can see example 37 here. I want you to find the extreme value of that. Well, I mean, actually, I should say the maximum and minimum values of that. But well, when you say max or min in the same word, we're gonna say extreme. We're gonna say extreme. All right, so now figure 3 here. This is the, well, if you put y squared minus x squared into the computer or something that you can graph, you can see the graphic online, you're gonna get this picture. Well, let's skip the picture first. Let's look at the equation. We are trying to get the critical point from this and then use a second derivative test. Again, I have f here, so I'm going to differentiate one time with respect to x. So I get negative 2x, right? And then I differentiate one time with respect to y. I get 2y. Sounds good because this is the function is so simple. And then now I have to find the critical point, we set up fx equal to 0 and y equal to 0, right? Once you set, fy equal to 0. Well, you set up this thing because you want a critical point. That means you have negative 2x equal to 0 and 2y equal to 0, which means actually x equal to 0 and y equal to 0. Well, the conclusion here is going to be 0, 0 is a critical point. So the point that is the candidate for max and min is 0, 0. All right, this is not that hard. The next step is, well, we're gonna do the second derivative test for this thing. So let's compute f double prime x first. F double prime x is gonna be negative 2, right? F y here gonna be 2, and f xy gonna be 0. Well, this is the thing that I can compute by just carry the thing here and here, differentiate one more time, and I get that. So now I have b, which is fxx times fyy, and then minus fxy squared, and this is going to be negative 2 times 2, and then minus 0 squared, which is negative 4, which is less than 0. Well, if you go back to the theorem says that once you get d, that you get less than 0. This is going to be the case that your critical point is called a saddle point. A saddle point means it is not a local maximum and it is not a local minimum. I mean, the point AB does not give local maximum or local minimum. Well, that means the conclusion going to be, well, by the second derivative test, you conclude that 0, 0 is a saddle point. Well, you can use the word saddle point. We understand that it is not a maximum. Saddle point, well, in Thai, if you are a Thai student, in Thai it's called Jup Anma, which, because if you look at the picture here, you can see this is like the saddle, right? The saddle thing, because, well, at the point 0, 0 here, well, I mean, this is actually 0, 0, 0, because we will in 3 dimensions. Well, at the point here, well, when x and y equal to 0, you didn't get maximum and minimum. So the picture is going to be like that. So you have something like in one dimension, you have it is max. In another dimension, and well, I don't know what to say, but well, if you use a plane to cut this picture, well, if you cut with respect to x-axis, so you're gonna get maximum. If you cut with respect to y, so you're gonna get minimum or something like that. It's just, you can see from the picture that this point is not max or min. It's just a critical point. Well, this is the case of the saddle point. Sometimes when you get a critical point, you could have a saddle point. So saddle point, this is not max and min. Sounds good. All right. And that's all for the basic of the second derivative test. I think we have about 30 minutes left, so we can do two more examples. All right, so let's do two more examples, okay? And then we're gonna stop the lecture. All right, well, 38 and 39, yeah. Two more and then we can, I think that's about the time. Two more and then we are good for today, good to go. All right, let's do number 38. So number 38, we have, well, the question say, find all critical points of the following function, and then you classify them as a minima, maxima, or saddle point. Well, start this question. This is the similar question that I can ask you on the exam. We're going to be something like this. So find the critical point first, and then check if it is max, min, or saddle point. All right, so the first one is, you have this thing. Well, you do not need to draw a picture because I didn't teach you how to draw a three-dimensional graph. So technically on the exam, you cannot draw a picture as well. You have to identify the pattern of maximum, minimum, and saddle point from just the equation and second derivative test. Does it make sense? That is the only tool that you have, so you have to do that. All right, so first of all, I am going to differentiate this function. So differentiate with respect to x. So the only thing I care is here and here. Other than that, constant. So I get, what did I get? -2 plus 2x, right? And then f differentiate with respect to y. All I care is this and this. Other than that, they are constant. So actually, this is actually 2y. Wait a second. -6 plus 2y. All right. So from here, we set up the equation fx equal to 0 and y equal to 0. So this yields 2x minus 2 equal to 0 and 2y minus 6 equal to 0, which give you x equal to, 1 second, x equal to 1, right? Because, well, everyone should be able to solve equation, right? And then y equal to 3, all right? Okay, 1 comma 3, well, this is the same function as before. Oh no, different function. Well, but anyway, the critical point here is x equal to 1 and 3. X equal to 1 and y equal to 3. All right, let's make a conclusion here first. A critical point is xy equal to 1, 3. All right, this is my critical point. Well, this is my candidate for max and min. All right, so we are going to compute f double prime f partial derivative with respect to x 2 times. So you get 2. Pretty similar to the previous one though, actually, 2. And then this is 0. All right. Well, this is similar to number 36, I think. You get d equal to that pretty boring because it's too easy. And this is going to be 2 times 2 minus 0, which is 4. And then greater than 0, right? And then if you consider fx equal to 2 less than greater than 0, well, this is actually by the second derivative test. Uh, 1, 3 give a local minimum. You know that this is a minimum because the secondary test, you get d greater than 0 and fx greater than 0. Well, when you have this thing, well, one thing that you have to be careful is if you compute f13 here, so this is what you get. You're gonna get 5 minus 2 times 1 minus 6 times 3 plus 1 square plus 3 square. Well, what I did is just I plug in this, the 0.13 into the function here. If I plug in that, so I plug in here, and if I manipulate that, so I'm gonna get number 9. Oh, sorry, number, well, let's say 5 minus 2 minus 18 plus 1 plus 9. Well, that is actually negative 5. Okay, okay, negative 5, good. And then after that, well, the negative 5 here, this is actually going to be the minimum value. The minimum value is 5. The minimum value is negative 5, and it is attained at the 0.13. Does it make sense? That is the meaning. Because some of you do not understand, and some of you understand that the minimum is number 1 and number 3. No. Well, note here, the minimum value of f is negative 5, and it is attained at the 0.13. Sounds good? So the minimum is actually negative 5. Well, if you want to find the value of the minimum, you just need to plug in the point to that function, and it will give you the minimum value. Well, what we did is just we solve for the critical point. We know where to get the minimum or maximum, but we have not compute the maximum and minimum. Well, on the last line here, I just compute it. F13 equal to negative 5. Sounds good? All right, any more questions? Okay, so I think we still have one more example 39 here. Well, this is going to be a little bit harder compared to the previous one. Well, we're going to look at something more complicated. For this question, we have x cubed. So you're going to, this is going to be an upgrade question because you look at the cubic equation. So it's going to be the one that you have more than one critical point. So we are going to look at this example together. All right, so let's do it. Well, here I have this function, right? So we're gonna do the same thing as before. We're gonna differentiate one time first. F subscript x, differentiate with respect to x. So I get 3x squared. Well, you have to be careful now. X cubed is 3x squared, and then 3xy squared I differentiate with respect to x. So I have 3y squared. All right, and 3y squared here, no x, I get 0. Here I have negative 15x, negative 15, then plus 0. All right, that is my partial derivative with respect to x. All right, next is partial derivative with respect to y. All right, so I'm gonna use another highlighter. So let's do the green one. All right, here 0, right? And then 3xy squared. All right, this is 6 times x times y because I differentiate with respect to y. And then this is going to be 6y. All right, what else? The remaining term, constant, so you get 0. All right, here you have 6xy plus 6y. All right, interesting. Because this question, you get a little bit more complicated equations. So let's see how to solve it. So we're going to solve for a critical point. Let's say solve for a critical point. So let's see what you get. Well, there could be the case that you have more than one critical point. So let's see. Well, you set up the equation 3x squared plus 3y squared minus 15 equal to 0, right? And another one that you have 6xy plus 6y equal to 0. So what do you get? So let's start from the second one here. 6xy plus 6y equal to 0, it seems that you can factor out y, right? Because y is a common ratio thing. Actually, you can pull out 6y. So you 6y and then x plus 1 equal to 0, right? Because you see you have a common thing, so you pull out 6y, so you get 6y times x plus 1. And that means, well, if you have two numbers that you multiply and then you get 0, this means 6y equal to 0 or x plus 1 equal to 0. Good? Well, because two things and then the product is equal to 0, that means either one must be 0, right? So that means 6y equal to 0 or x plus 1 equal to 0. And that means y equal to 0 or x equal to -1. All right, this is your conclusion for the equation that I highlight in red. So at the end, you solve, you get y equal to 0 or x equal to -1. How about the one that I highlight in yellow here? So you have 3x squared plus 3y squared equal to 15. If you divided everything by 3, so you have x squared plus y squared equal to 5. Just make the number smaller. Well, at the end, you get that x squared plus y squared equal to 5. So the critical point that you want is going to be the point that match with the equation that I circle, x squared plus y squared equal to 5. And it must be the case that y equal to 0 or x equal to -1. So when x equal to -1, well, if x equal to -1, so x squared plus y squared equal to 5 becomes -1 squared plus y squared equal to 5. And that means 1 plus y squared equal to 5. That means y squared equal to 4. That means y equal to plus or minus 2. So when x equal to -1, y equal to plus or minus 2. So this means the critical points for this case is r, because you have more than one, right? X equal to -1, y equal to -2, and x equal to -1, y equal to 2. So when x equal to -1, you have two critical points. Good. And when when y equal to 0, let's see what you have. X squared plus y squared. This is going to be reduced to x squared equal to 5, right? Because y equal to 0. And that means x equal to plus or minus square root 5. Okay. From this case, the critical points are x equal to square root 5, y equal to 0, and x equal to negative square root 5, y equal to 0. Actually, from this equation, the function of two variables here, you have 4 critical points. All right, let me highlight in light blue here. 1, 2, 3, and 4. Well, you have 4 critical points. Good. All right. To sum up, we have 4 critical points. Well, this is perfect for the exam. We have 4 critical points. Well, this is the question that fit well on the exam for sure. We have four critical points, which are -1, -2, -1 to square root 5, 0, and -5, 0 here. Well, to reduce your work here, because if you have to do each of them, it's gonna be, too long. So we're gonna make a table. So let's see what I did here on the table. You ready? All right, so this is the same function as before. Well, we're gonna make a table here. Well, this is going to be my critical point. Well, we have 4 critical points, which is -1, -2, right? -1 and 2, negative square root 5 and 0, and square root 5 and 0. So we have critical point 4 critical point here. We're gonna compute f double prime x here. 2 times fxx. And then after that, we're going to compute fyy. And after that, we're going to compute fxy. Right? And the next column, we are going to compute d, which is equal to fxx, fyy minus fxy squared. Oops, fxy squared there. And then at the end, we're going to make a conclusion. All right, let's see what you get. All right, so first of all, when you have that function, so we already compute the first derivative and the second derivative here. So I'm gonna copy from this page, gonna paste it here. This is my f subscript x and f subscript y. This is from the previous slide. You can see that, right? So, I mean, the font is so small, but actually, I think you can see that. Well, when you differentiate with respect to x one more time, so here you're gonna get 6x, all right? And does it make sense? This is just 6x. Well, fxx here gonna be 6 times x, because you differentiate 3x squared plus 3y squared minus 15 with respect to x one more time, you get 6x. And then fyy here gonna be the one that you differentiate with respect to y one more time. So actually you get 6x plus 6. Right? You just differentiate fy with respect to y one more time. And then fxy here going to be the one that you differentiate with respect to y. I mean, after you get f subscript x, you differentiate with respect to y one more time, you get 6y. All right, so we're going to compute that. So on the first column, you have fx equal to 6x. So this number is going to be -6, -6, -6 square root 5. And that is going to be 6 square root 5. Can you follow me? Good. And then the next column, I'm going to do the highlighter to be the pink one here. 6x plus 6. So that means here I'm going to get, well, when I plug in x equal to -1 into the function that I highlight in pink, so I get 6 times -1 plus 6, which is 0, right? And then x equal to -5 here, so I plug in, so I get -6 square root 5 plus 6, -6. No, this is just 6 square root 5 plus 6. Okay, and the next column that I get 6 times y, all right, which is -12, 0, and 0. Right, so you have everything in your hand now, and then now you compute your function d, which is going to be the first column times the third column, and then minus the second column square. All right, this is what I call the first column. This is the third column. You multiply it together, and then you minus, determine the middle square. All right, so you're gonna get sounds good. Did you do something wrong? No, okay. Oh, okay. I'm sorry. I missed the column. So again, so go back again. Sorry, this is going to be this column multiply this column. I'm sorry. This column multiply this column, right? And then minus this column square. Okay. I switched the order. Sorry. fxx multiply fyy and then minus fxy square. All right. So let me see the chat. Right. Yes. Nida and Rohit. Thank you for correcting me. So I'm too nervous. So that's why I say that. So, but fxx multiply fyy and then minus this thing square. All right. First of all, so I'm gonna get -6 multiply 0 and then minus -12 square. So actually the first, well, you do that for every line here. So that thing I'm gonna get -144, right? -144. So the second one, -6 times 0, you get 0. And then minus 12 square. So this is actually negative 144. And then, well, this is the third one is the hard one because you have to multiply that and that. But once you multiply that and that, you subtract this thing square, which is 0 already. So you just need to multiply the first and second column. So actually you're gonna get, let me multiply that. So I actually did it at home, you know, when I prepared the lecture. So I get 180 minus 36 square root 5. So you have to be careful when you multiply, but you know, take your time when you do it on your homework or exam or something, because this may give you a few minutes to multiply this thing. All right, next you have this, multiply this, and then minus this thing square. All right, so this is going to be 180 plus 36 square root 5. So, wow, you get everything already. So now you can see that this is less than 0. So this is saddle point, right? Every time you get the less than 0, so this is saddle point for sure. This is less than 0, so this is actually saddle point. So the two critical points here give you saddle point. All right, next, 180 minus 36 square root 5. Even you don't have the calculator, you should be able to identify that this thing is positive, right? Because 180 is so big, 36 square root 5, square root 5 is just 2 point something, because square root 4 is just 2. Square root 5 is 2 point a little bit. So 36 times 2 point a little bit. Well, it cannot be bigger than 180 for sure. So this thing gonna be positive. And this thing gonna be positive because the big number add together. So this thing is positive, this thing is positive. Well, it could be local max or local min. However, you go back to this thing, and this will tell you which one is max, which one is min, because this thing is bigger than, this thing is less than 0. This thing is bigger than 0. So if you compare to the second derivative test, this is the conclusion by second derivative test. Well, you can see that the point negative 5, 0, this is actually local maximum. How do you know this is local maximum? Well, f (a) is less than 0 and d bigger than 0. This is local max. And the last point here going to be local minimum. All right. Well, if you can draw this table, I'm fine. You get full credit for sure. If you can complete this thing on the exam, maybe on the exam, I am going to give you a table and then you have to fill in the table or something. Well, and that is, you know, the last example for today. Well, you can see this is not hard. It just, if you understand the process, you can see the second derivative test is just simple. You start from f, differentiate 2 times, trying to get the discriminant d, and then conclude the pattern from there. Sounds good? Next Monday, we're going to come back to example 40. This is the example that you can relate the thing that you learn to the real life. So I'm going to explain this example on Monday, and then we're going to move to integration, the next topic. All right. Well, you don't have any questions, so good luck, everyone. The take-home quiz will be distributed in 15 minutes, and then you have 72 hours to complete it. So be sure to submit it on before Saturday at noon. Well, this is the hard deadline. If you miss the deadline, so you get 0. So make sure you complete everything. Well, maybe save the last 10 to 15 minutes to upload as well, because you know some of you are gonna have an excuse all the time. Oh, because my internet is slower, I cannot upload on time. That is not an excuse, because I give you 72 hours. You should complete it like within the time. Good luck. All right, I'll see you on Monday. Thank you. Oh, let me see the chat. Pakawat say what? Could you please explain example 7 in the chain rule again, please? Okay, Pakawat, do you need a chain rule? That thing. So can I come back
yes ครับ
to you okay 1 second well we have time here so I'm gonna do well you can leave but Pakwat if you wanna look at that which one which I mean which part do you have a question on that
the second part อาจารย์
okay start from this line right well
yeah.
when you have is this good for you
Yeah, yes no like
1
I
second
don't
which one I mean
I don't understand the partial C over partial Y the part where you did the tree diagram
okay so okay here one more time let's take a step back and look at that so let's suppose that I want to compute the thing that I box here okay and some of you can have a hard time why this box when you do the chain rule and it's get to this bracket right this is the question
yes,
mainly
yes, yes.
I think why this thing can come to that well if you remember well I told you to draw a tree diagram because 1 second let me mute you a little bit so the thing is that when you have something on the top level here which means curl C by curl Y is on the top level here you have this thing as a function of x and y this thing as a function of I and s x is a function of I and s y is a function of I and s right and then you can see that the thing that I highlight in yellow here this is inside the parentheses if I want to differentiate the thing inside the yellow thing here with respect to r so that means this is on the top level here with respect to r I is on the bottom level here so I have to differentiate the yellow thing so you can view this thing as a yellow thing first if I don't care anything so I'm gonna say hey this is my yellow thing I don't care what it is this is my yellow thing so you're gonna get differentiate yellow thing here with respect to x and then multiply differentiate x with respect to r and then differentiate yellow thing here with respect to y and differentiate y with respect to r this is because of the T diagram here right you differentiate the box here with respect to r by via x and via y so that's why you get this multiply this is the first chain right 1 second here this is the first chain and here this is the second chain and then because the thing that I just put the orange box there this is actually curl C by curl Y here so this is curl C by curl Y that is why I say hey let's do that but I just put curl C by curl Y here does it make sense make more sense here
yeah
all right but well the hardest part is because of the notation the notation is getting messy right because you have something inside here and here but the concept is just the basic chain rule but the thing that make it looks hard is just the notation and then the next step I just group this thing up to be that group this thing up to be that is why I get this thing or I mean Pakawat if you feel like you still confused or something try to do this 2 example and you can send me an email so I can check it or I have not upload I mean I have not make a solution for this thing but well for those of you who want me to look at your work you can do it and just email me so I can look at it and I see if and I can say this is correct or not sounds good
okay
all right any more question for Villa Rohit Gochumon what no good
no thank you
okay crap okay well I'll see you Monday